Okay.
Okay.
And let me share my application. Okay. So I was trying to get some questions for us to work on. Let's see. Hold on. Let me make sure my questions actually uploaded. Okay. For some reason, I'm not seeing the questions here. Okay. Well, I don't know where the questions went. Oh, there they are, right here. Uh-huh. Great. Okay. So I have this here for when I need to, I'll come back and look at these questions. So you guys can see the questions, right?
Yes.
Okay. So I have the chat page open so that if you guys have any questions about what I'm going over, because we're going to be doing a lot of math, if you have questions, feel free to ask me at any point or type it in the text, and I'll be looking at that constantly, you know, like, on YouTube. I consider myself a Blackboard influencer. That's not a thing. Nobody's on Blackboard unless they're in class, right? But anyway, yeah. So let's go ahead and start the chapter. I really feel like I'm a YouTuber right now, even though I'm not on YouTube. I'm just on Blackboard. But yeah. So anyway, that's what that quote unquote joke was supposed to be. Yeah.
Like one of those
if you if you missed it, then it wasn't funny. You know the YouTube influencers, Blackboard influencer, but nobody's really watching Blackboard unless they're in class. Yeah. Anyway, let's go ahead and start. Chapter 3, unlike Chapter 2, is not introductory, so we're getting straight into the measurements. And so, like before, this chapter has a long list of objectives. So if you're wondering what we're going over, I'm not going to read all these objectives. You can go ahead and look at each and every one of these. There are so many pages, but the most important thing is this chapter is all about measurements and chemical calculations. So it's showing us how to use the different methods of, I guess, the different mathematical calculations we do in chemistry and how we handle measurements. At some point, I was trying to see if I could get some measurements for us today. I wasn't able to get any in time. I had students from my other class emailing me a lot. Long story short, I'll try to make sure, I'm going to write myself a note right now for our class on on Thursday, for me to get some measurements. Okay? So for our class on Thursday, I'll try to get pictures of different measurements and then see if we can practice together how to read the measurements when you have different scales. Okay?
Okay.
So let's yes.
Oh, sorry.
Does someone have a question? Does someone have a question? Okay.
No. I'll just commenting. That's all.
Okay. So we're going to go ahead and start with scientific notation. So building up on what we talked about before in chapter 2, I teach 3 different chemistry classes. So this week I can't remember what I said in each class because last week was like one big blur. But I will just say that when you are in the lab and you're taking measurements, one of the key things you want to do is know how to communicate your measurements to other people. If your numbers are very large, so if you have very large or very small numbers, we tend to use scientific notation so that we can minimize errors. So the goal of using scientific notation is to minimize errors. So if your numbers are either very large or very small, we try to use scientific notations to represent those numbers because we have a goal, minimizing errors. Okay, so with this goal in mind, we're going to practice how to convert from standard numbers to scientific notation. So we're told when you're looking at scientific notations in general, the number has 3 parts. There is the base number, this is called the base. You have the 10, which is based on the logarithm with a base of 10, and then you have the exponent. Okay, so 3 parts. You have the base number, then you have the 10 raised to the power of the exponent. So the base number, also called coefficient, tends to have their rules to what this value can be. We're being told here this number is equal to or greater than 5 and less than 10. So if you were to place this number here in what's it called, limits, you would write a dot b c d as greater than or equal to 1, because it can be equal to 1, but it has to be less than 10 and not equal to 10. Okay, so whatever number you assign this number to be, it has to fulfill this requirement. This is a mandatory requirement. Okay, this first number, coefficient base number, has to fulfill that requirement. It can be equal to 1 and between 1 and 10, but not equal to 10. And then, of course, we have the exponent part. Well, you have the 10 part, this part here, that is based on logarithm number, the log of base 10. And then you have the exponent. The value of e depends on what the original number was. E is negative if the original number was small. So it's negative if number was less than 1. And it's positive if number was greater than 1. Okay, so we'll go through rules of how to, well, not really rules, but we'll go through practice of how to write scientific notation, being given a standard number or a basic number. Okay, remember the purpose here of writing scientific notation. We tend to use it for very, very large numbers. It makes it easier for us to minimize errors, and in some cases, scientific notations help us to present our numbers in the proper significant figures. Okay, so having that, it shows you here, we're going from converting from a decimal number, which is what we call the standard or regular number. So this is a standard number, to scientific notation. So we're told here, rewrite the number, place the decimal after the first non-zero digit, then write times 10 power. So I'm going to go through all of this, and then we can read the rules to make sure the rules make sense. Okay? Because when you read rules in chemistry, they don't make sense until you start to apply them. So I'm going to be going straight to this page. Let's say we have this number here. 1, 2, 3, 4, 5. Yes, I went that way. 6, 7, 8. This is a large number. And we're asked to take the standard number and convert it to a scientific notation. Okay? So you examine your number and you ask yourself, does the standard number have a decimal? In this case here, the number does not have a decimal. So if it doesn't have a decimal, the rule said place a decimal point to the right of the last non-zero number. So I put a decimal here, and you want to move the decimal all the way to the left, well, not extremely to the left, but to the left until the number you have is between the recommended values, which is between 1 and 10. So you're going to move this 1, 2, 3, 4, 5, 6, 7. I move this decimal point 7 times to the left. So when I do that, I have this number 1.2, 3, 4, 5, 6, 7, 8. This number I have fulfills the requirement, which is a dot b c d has to be greater than or equal to 1 or less than 10. This fulfills that requirement. And then I take the number multiplied by 10 raised to the power. So I have to figure out how many times I move the decimal point, right? So I said 1, 2, 3, 4, 5, 6, 7. So it was 7 spots. So I'm going to raise it to the power 7. Okay? I am not going to put a negative up here because my original number that I started off with is greater than the number I have here in the base position, or the, what they call it? The coefficient position, right? So this coefficient position or base position is less than my original number. For that reason, I will leave this as 10 power 7. Okay? If I had a different scenario, say I had 0.000001, and I were to convert this standard number to scientific notation, This time my number starts off with a decimal point. Now I have to move my number not left but to the right until I have one non-zero number to the left of the decimal. So I'm going to move it 1, 2, 3, 4, 5, 6, right? And I end up with 1 point, and you can write it like this, okay, times 10 power. I move the decimal 6 spots. But since my number, my base number, or my coefficient number is greater than this number here, I'm going to put a negative here. So that when you input this in your calculator, if your calculator, like mine, is not set to scientific notation, it will actually give you this number right here. Okay? Same thing with this. If your calculator is not set to scientific notation and you put this in your calculator, it will give you this number. Okay? So the rules essentially tells you what to do. We write the number, place the decimal in the first non-zero number, write times 10, count the number of places the decimal. Count the number of places the decimal in the original number moves to its new place in the coefficient. Write the number as an exponent of 10. Compare the original number to the new coefficient. If the coefficient is smaller than the original number, the exponent has to be positive. If the coefficient is larger than the original number, the exponent has to be a negative value. So all I did was go through these rules. So I'm going to move on then to this part right here. This shows you guys how to convert from scientific to standard notation. So I've given you guys this example real quick. Let me go ahead and check and see what kind of questions I have here, because these are really about significant figures. And let me see. I don't have scientific notations here. Oh, no, I don't. Okay, but since I have this number here, let's say you were given this number and asked to write this number in scientific notation. How would you do that? What would your answer be?
Would it be 5.6775 times 10 to the 7th?
1, 2, 3, 4, 5, 6, 7. It has to be -7 because
Oh, yeah, negative, yeah.
5.6775 times 10 to the -7, because the base number you have here is bigger than this number here, right? If you're not sure, put the number in your calculator, and if the number comes out different, you have the wrong sign, okay? Any questions about this? Yeah, I'll keep coming back and forth to make sure we're getting some practice with this, okay? Because with the PowerPoint, the answer's already there. It's very easy to kind of just, check out. Okay, so in this number here, we're being asked to convert that number to scientific notation. Just like before, they went ahead and moved, these are commas, not decimals, right? So you place your decimal at the end and move your decimal 1, 2, 3, 4, 5, 6 spots to the left, right? So your number will be 3.672199 times 10 power 6. Since this number here is less than the original, you leave this as a positive. Okay? And that's how they get this number right here. In this one here, once again, convert this number to scientific notation. You want to move your decimal 1, 2, 3 until you have one non-zero number to the left. You're going to rewrite that as 4.61 times 10 power. I moved 1, 2, 3 spots, 3 spots. This number is bigger than the original number, so that will be times 10 power -3. Okay? Once again, if you're not sure if your answer is right, place this in your calculator. If it gives you the original number, you entered it correctly. Okay? Okay. So where was I? Oh, these are some other questions I had. So let me see. Based on this, so I'm going to erase this. I wrote this in the past. I'm reusing the slide because I'm unable to download the PowerPoint slides. So if we're given scientific notations like this, how do you write standard numbers or standard notations? So being given this one here, you will start with the base number or the coefficient, right? 5.12. And this time, you have to move your decimal 3 spaces to the right. So I move it 1, 2, 3. Okay? Since there's nothing here in this empty spot, you will add a 0. So the standard number that is produced when you have the scientific notation here is equal to 5, 1, 2, 0. You can leave this decimal off. The decimal ends up right here, so you can leave it off. And this will be your standard number right there. In the case of this number right here, let's see, 1.7, and it says -5. So I have to move the decimal point 5 spaces to the left. So this one here, I'm going to move it to the right. Based on this number here, I'm going to move it to the left, and then let's see what I get. To the left, 5 spots. 1, 2, 3, 4, 5. Right there. And I put in zeros right here. 0, 0, 0, 0, 0. So my number ends up being 0.000017. Okay? Once again, if you put this number in your calculator and it's not set to scientific notation, it will produce this number. When I'm not sure, I double check it. Okay? Since I have to move 5 spots to the right to get this number, I try to move it back again. 1, 2, 3, 4, 5. Okay, I did it right. I have the right number of zeros. Okay? Any questions about this? How to go from standard to scientific and then vice versa? Okay. If I have no questions, I'm going to go ahead and move on. In this question here, oh, okay, I see what this is. It's a lot of zeros. In this question here, they want us to, I know the answers are here. Wait, what happened? I know that the
I
answers.
think it's a whiteout rather than an actual eraser. I don't know.
Is that what I did? I think it was slow. My
Okay.
all my equipment is getting too many miles. I'm using them too much because I'm teaching a bunch of classes. Yeah, maybe my
Oh.
internet is slow. I don't know.
No,
Okay,
yeah, that can happen.
yeah. So we're trying to convert this number right here to a decimal form, right? So I can't see this. I think the decimal is right here. The arrow is obscuring the decimal. So I'm taking this right here. So in this case here, I have to move the decimal. This is my starting number, 3.49. I have to move it 11 spaces to the left. Ooh, okay, I can do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oops, that was it. 11, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right, that's all I needed. That's what, great. I knew something will happen, something like that will happen. I can do this again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, fine. This is a new decimal spot right here. Okay, hopefully I can just erase. I give up. Okay, there. This is a true decimal spot. Online, I can do this. Okay, y'all know where it is, right? This is the truth right here. Everything else is okay. So I'm gonna put in my zeros. I put my 0 here, 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 the 0 here, and finally a 0 here. Okay, so that becomes your true value, which they have over here. Once again, in this case here, 5.16. We have to move the decimal to the right 4 spots. So you got 1, 2, 3, 4. Yeah, 1, 2, 3, 4. Add the 2 zeros. This becomes your final answer. And this is your final answer right here. Okay? So your homework is really not that bad. Well, when you ask me, it's not that bad. Okay. How do you input scientific notation in your calculator? In your calculator, it's very important to find your exponent key. In my calculator, I proudly own a TI 34. It was I think it was $12 on Amazon, and I am proud of it. Okay, I don't have any of those fancy calculators that they have out there. This one works, and it's blue, my favorite color. Okay, So on my calculator, I do not have the, let's see, what key do I not have? I do not have the EE or the EXP key. Instead, I have the times 10 power N key. I deliberately selected this calculator because I wanted the times 10 power N key. So when I actually put numbers in my calculator as a scientific notation, say my goal is to write 5.4 times 10 power negative 6. I input it this way, open parentheses, 5.4. I press my times 10 power N key, my exponent key, and then what do I have here? I have this key as my negative, and then 6, like that, and then close parentheses. Okay, actually, no, there's one more step. I have to use the right arrow, close parentheses. I have to plug in all these values here just to tell my calculator to input this number. And when I press equal or enter, I get this number up here. Okay? When I do it this way, I always get the answers right. If you use 5.4 and then use times the operation and then 10 and hat negative 6, this may give you errors. So I strongly discourage you guys from using this. Use the EE or the EXP or this if you have it. Okay? Any questions about that? So once again, I show this here. Okay? I show this here. That if you're trying to input this in your calculator, you may have to input it as open parentheses 4.11 EE plus or minus and then 11 close parentheses. Okay, you want to make sure, because the thing with chemistry, your homework and sometimes your exam has multiple choice problems, and some of the wrong answers are based on misusing your calculator. So just because you got the answer doesn't make it the right answer. You may have put the numbers in your calculator wrong. Maybe parentheses were left out. Okay, so it's important for you to input the numbers correctly. Any questions about this? Okay, so we will move on to the next part, which is dealing with conversions and quantities once you're given a problem. So we're told here, when you solve quantitative chemistry problems, problems with measurements and numbers, think of the quantity as the product of the value and a unit. So here, if you're given, say, 7.12 miles, think of these two as a number and a unit that are multiplied. That means when you're working out a problem, the unit can be canceled out when the number remains intact. Okay? So let me see. Do I have a place to work this out? Oh, I wrote this for later on because I know you guys have a lab you're planning on working on. Is your lab for this week dimension analysis? Is that your lab?
I think so.
Okay, right. So what I mean by that is when you have measured quantities like this right here, there is a value, which is the number, and the unit. Think of these two as being multiplied. So the example they give us here, all we're doing here is taking 50 minutes and converting 50 minutes. It's hard for me to multiply, to modify that. This is a picture, and so I can't really modify it. But what they're asking us is to express 15 minutes in seconds. 15 minutes, convert this to seconds. So what I'm going to do here is I'm going to use conversion factors I know about time and use those to convert from minutes to seconds. Can anybody give me a conversion factor that has minute in it? If I have 1 minute, how many seconds do I have in 1 minute?
60.
Okay, so 60 seconds. Okay, I should write this just like they have over here. So I'm starting slow. We're just kind of warming up, right, as we're getting our bearings. Their idea here is this number and that unit are multiplied to each other. Same thing with this number and that unit. Okay. In our conversion, you always start with what's given. So I'm going to start with 50 minutes. That's my given number and my given units. And then I'm going to use the conversion I have. The conversion I have has to have at least the ideal conversion unites or equates the given unit to the wanted unit. So technically, this is the ideal conversion factor. Okay, once again, this is a judgment from me. It's ideal because in one equality, you have both your given units and your desired units, with this being my given and this being my desired. So now I get to use my conversion equality as a fraction. Okay, since I have minutes up here, I have to put the minutes on the bottom. So I take this number. Even though they're multiplied, they come in as a combo. So I write here 1 minute, and then the 60 seconds goes on top. 60 seconds. Okay, the minute and the minute have to cancel out, and what I'm left with is I am left with whatever number I get with the unit seconds. Okay, so what they mean by the units and the numbers are multiplied is that I can cancel out just the unit part without affecting the number. So you see here, what I'm left with is 50 times 60, and this should be in seconds. So when you multiply it out, you get this is 30, the two zeros add up, and we get with seconds. And this should be our answer right here. Okay? Any questions about that? Yeah, I thought by this time we'll be ready for this. No, we're not. So I'm going to leave this here for right now. We'll come back to this, okay? If we don't, just remind me. I'll write it somewhere here. Remind me of that conversion. Because I was trying to find a conversion where you're going from a derived unit to a derived unit, and it was hard to find those. Chegg and something lib and all those websites are taking all the good stuff. And now you have to pay or register or sign up for something just to access all the good stuff. Okay? And I refuse to sign up for that stuff. Okay. We're gonna work on this problem here. So on this problem here, they give you an equality. And even though I know it's worked out right here, I'm going to work it out from scratch. First of all the formatting is messed up here, so you can ignore this for right now. We're told the third oldest horse racing track of its kind in the United States is the 8-furlong Pleasanton Fairgrounds racetrack in California. Okay, the measurement we care about here is 8 furlong. Who uses that? They do. What is 8 furlong? What is this length of the track in rods? So then they tell you 0.025 furlong is equal to 1 rod. So they essentially told you 0.025 furlong is equal to 1 rod. And they want you to go from 8 furlongs and convert this to rod. Once again, since we're going from furlongs to rod, okay, this is once again the ideal conversion factor. Why ideal? Because in one equality, you have both your given unit and your desired unit. That's what you want to have. Does it always work that way? No, it doesn't. Okay, so you adapt. So in this case here, my given unit is furlongs, and then I have to convert. So I'm going to use this equality as a conversion factor. The number and the unit goes together on the bottom, 0.025 furlong. And on top, I have 1 rod. Okay? Once again, this is still the warm-up. Do all conversions work out this simple? I wish they don't. But we're still warming up on how to use the conversion factors, right? And they gave us a very ambiguous conversion like this. So once we're done, our answer will be in rods. Since you have a numerator number and a denominator number, just divide. So you take 8 divided by 0.25. And our answer will be 320 rods like they got. Okay? So this is our answer right here. 320 rods. Once again, number I can personally not relate to, but this is the answer. Okay. Any questions about this? So I thought I posted the conversion chart, even though I don't have it right here. I thought I posted it. It's not on the, I don't think it's on the PowerPoint. No, because of distortion. Let me see if I have it on here. Let me minimize this. Because I tried to post it on your, no, this is the wrong. For this class, the chapter starts on 2, so the second chapter is technically 3. It's something I have to keep remembering all the time. Oh, there it is, the conversion table. So just in case, I have a conversion table right here. This is a very useful conversion table. I will suggest, if possible, to have this printed out so you can refer to it whenever you need to. Let me see. I have so much going on, right? Where's my conversion table? Right here. So I'm going to have this somewhere in the back. When you need to, this here has the conversions by category. So we have length conversion, mass conversion, volume conversion, whatever you need. They do have heat conversions, pressure conversions. They don't have time conversions because they're assuming you are experienced with time, right? And so they have all these right here. So just in case, let me see. I'm trying to have layers of files here. Excuse all the crazy stuff I'm trying to have open. I just want to be able to access these when I need them. So I know somewhere here I have the conversion chart. Yeah, so I have this. I have this. The conversion is lost right there. Okay, so as I need it, I'm going to refer to the, oh, yeah, I'll figure this out eventually. As I need it, I'm going to be clicking on whatever I need, okay? Once I figure out where it is, let me put it on the side. I think it'll work better over here. I know, I'm trying to accomplish a lot. So this will be down here, and this will be, the other one will be over here. Yeah. Okay. So as we need to, we will grab the conversion chart. It's right here, and y'all can see it right here. As we need to, we'll click on here, have access to it. So what I want to do here is I want us to recognize that this table here has a bunch of equivalencies. And what an equivalency is, it says right here, an equivalency is two quantities that are equivalent in value. So they're two measurements of the same object with two different units. So you have different units and probably different values. But these are representing the same object. Okay, does someone have? Oh, thank you. You see the struggle, right? I really am trying to do so much. Well, thank you. Right, so right here, so any of these equivalencies can become conversion factors, right? Convert these to be the fraction based on what you're needing, and we can go from here, okay? So I want us to actually practice taking the equivalency and making it a conversion factor. The conversion factor is a tool. I was trying to explain this to somebody who doesn't take chemistry. And I was saying a conversion factor is kind of like cutlery. If you go to a fine restaurant, right? Apparently there's a spoon for soup and a spoon for dessert. Okay? I remember going to a fine restaurant. You got to understand the context. I am African. And being African, you use your hand. Well, in some cases, we eat with our hands and we use our hands for a lot of things. If you want to eat something like bread, you use your hand. Pizza, your hand. Rice, your hand. Soup, you can use your hand. Okay, so I go to a fine restaurant and they're like, well, there's a salad fork and the fork for the main meal and the fork for dessert and a spoon for this and a spoon for that. And I'm looking at them like, wow. So at some level in my mind, the conversion factor is there is one for every purpose. In some cases, you need more than one to accomplish your full conversion. So you get to pick from here. And by the way, this is not comprehensive. That means there's a chance this table may not meet the needs you have. It has some conversion, but not every conversion possible. Okay? So let's go right into it. Let me go ahead so we can see how this works out. Here they're showing you how you use the conversion, how you go from an equality to a fraction. You already saw me do that, right? This equality here can be a fraction. Once again, these are equal to 1 day. 1 day can be measured in days, it would be 1 day, or in hours, 24 hours. You can use this equality as a fraction, either the first fraction right here or the second fraction right here. Which is correct? Both. Well, how do you know what's correct? It all depends on the given unit. If the given unit has hours here, then it would be a good idea to use this form. If it has day, it would be a good idea to use this form. Okay? So I'm not going to spend a lot of time on this. I would rather practice this so you can get the hang of it, and then maybe you can have a question. So they go into the steps of how to read this. First of all, if you're given a problem, analyze the problem statement, look at your given value, determine the given quantity, the value in the unit, describe the property of the given quantity. Is it a volume? Is it a length? Is it a mass? Once you figure that out, describe the property of the wanted quantity. What are you looking for? Are you going from mass to volume, or are you going from mass to mass? Because the approach you choose depends on the goal, where you're heading, right? And then state the unit of the wanted quantity. The units will also help you pick the right path. Then the next thing is you want to identify the equivalencies or the algebraic relationship based on where you're starting and where you're going. Okay? So as needed, you would select your equivalencies from right here. Ta-da! You have the spread, length, mass, volume, and then when you're done, you set everything up, and then you solve your problems. Okay? Okay, so feel free to read the rest of this. Rather than reading what we're about to do, I would rather we actually practice this, and then we can read it when we're done. Okay? So we have an active exercise here. In our active exercise, let me go ahead and erase this. So I see I had some random questions right here. Here we're being told we have 672 hours, and this is time. They want us to go from 672 hours, and we have to convert this to weeks. Okay, I think I can do this, right? So I'm going to write here 672 hours, and we have to go from that and convert to weeks. So we're going from time to time. This is a time to time conversion. Okay, so how are we going to set this up? We need to find our conversion. So can you all tell me a conversion that has time in it? Or that has
for example,
hours.
oh, so you mean like 1 year and like 52 weeks? Like that?
Okay, yeah, 1 year equal 52 weeks. Now, this is not necessarily very useful to us because even though it has weeks in here, we would rather have something that maybe is bringing us closer to hours. So while this is correct, it's not very useful. This scale here is too large. It's not the 1 year here is not something in between hours and weeks. So we can start with maybe week and days. 1 week equal how many days?
7.
7 days, okay. So so the 1 week works with this time here, or this unit here, right? And the 7 days is something in between these two. So that works. As long as your other unit is an intermediate between the two units. Now I need something that goes from days to maybe hours. We can do 1 day. 1 day is equal to how many hours?
24.
24 hours, right. So the only reason why this one doesn't work is because the year is not a unit that falls between these two. So I can use these remaining two, though, these conversions here. Ooh, yeah, I can use these right here. So I'll set it up. 672. Once again, this is still a warm-up. I'll tell you when we start doing the actual chemistry conversions. Okay, so I got 672 hours here. I have two to pick from. I want to pick the one that has hours, so I can write it right here. This conversion here has hours, so we put 24 hours. And then here, this goes with this 1 day. Okay? Then up here, hour and hour cancels out. Now I have to use a conversion that has day in it. This is 7 days, and I have 1 week. Okay? Days and days cancel out. So when you do this conversion, your answer will be in week, even though your math is 672 times 1 times 1 divided by 24 divided by 7. Okay? Now, the reason why I had this divide twice, my cheap yet blue calculator understands these two numbers as being denominator numbers. If I write divide by and times right here times 7, it will put the 7 as a numerator and give me the wrong answer. It's very important to input the numbers correctly in your calculator, or all the work you're doing is not going to help you get the right answer. So let me see. After all this, I think I get 4 weeks. 672 times 1 divided by 24 divided by 7, I get 4 weeks. Is this correct? Yes. Look at that. Okay. So let's start doing conversions where we're using given conversions within the problem. Sometimes the conversion is given to you within the problem, sometimes it's not. In this case here, let me see. Okay. In this case here, the conversion is given to us within the problem. So let me go ahead and write this down here. We're told what this expressed in miles. So I'm going to write here, my wanted is some number in miles. I know it's a distance or it's a length. Okay. Will an automobile travel in 3 hours at an average speed of 62 miles per hour? So I'm given time as 3 hours, right? I'll put it as HR for hours. And I'm given speed as 62 miles per hour. Miles per hour. So when it comes to conversions like this, I usually say it took me a while to figure out the trend, which is we have two given numbers. So it's not really that simple where to start. The easiest thing to do is to start with a simpler number, the number that has the simplest unit. What I mean by simple here is the unit for this number is just hour. It's not hour over something or hour squared or whatever, just hours. So start here or start with this. Because this here is more complex, you can use it as a conversion factor. Plus the units are miles over hour, right? So before I do that though, I want to make sure my speed is a full fraction. So I'm going to write 1 here. Then I can start. Okay? Start with my simple number, 3 hours. Use my conversion, 62 miles per 1 hour. Since I use this number, I look at the unit they gave me and see if I can use it next. If I can use it, I'm doing good, right? The hour here and the hour here cancel out. Did I get my desired unit? Yeah, look at that. My desired unit is right here. I wanted miles. This is miles. All I have to do to get the number is take 3 times 62 to get my number. And my number will be some number, miles. So my number here is going to be 3 times 62 to get 186. Yes, 186 miles. Very good. Okay. We haven't started doing significant figures yet, so I won't talk about rounding up or rounding down. We're just trying to work our way through the conversion factors. This is a conversion factor. Okay. Anybody has any questions about this? Okay. So we're going to be moving on to this problem right here. I don't want to do this question because I do have some more harder questions. Because at some point, these questions do get very, in your homework at least, from what I looked at, they do get kind of tough. So before I get into this pennies and stuff, I want to see what we have over here. Can we do some conversions? Because you do have some conversions. Let me see this one here. These are all significant figure rules, and we'll get to that once again. We'll get to it. Okay. Let me see. Do we have some conversions? Oh, these are metric conversions. Not yet. You know what? I could. Yeah, these are metric conversions. So let's go over the metric rules first before we do that. Yeah, I am so eager to work on that, but we have to learn some more before we can do those conversions. I don't want to jump ahead. Okay, back to this question. We're told a little girl broke open her piggy bank. Inside, she found 2608, and that's written right here. So I'm going to rewrite it. Pennies. How many dollars did she have? So, let's see. With this one here, they want you to go from 2608 pennies to dollars. So you need to have the conversion factor, right? And the conversion factor here is $1 equal 100 pennies. So let me go ahead and erase this part right here. Okay. So once again, this is one of those intuitive conversion factors. They don't really give it to you, but they assume you know it. We're going from pennies to dollar. So I'm going to write my given number, 2608 pennies. And then my conversion factor, I have $1 equal 100 pennies. Since I have the word pennies up here, pennies must show up diagonally across. This is going to be down here. 100, $1. So once again, this is straightforward. You cancel this, divide these two, and you should get what? $26.08, right? So you take 2608 divided by 100. Yep, $26.08. Okay? So yeah, this should work out. So let me see. Oh, finally, the metric system. Okay. With the metric system, I'm trying to erase this. Let me look at this number I had. Yeah, we have to do the metric system first. So in the metric system, okay, the scientific measurements we have, remember how we use scientific notation to make sure that we don't have a lot of errors and to transcribe very, very large numbers and very, very small numbers? We use the metric system for the same purpose. So you have the 7 base units we discussed in chapter 2, right? The metric prefixes accompany the base units. So you tend to have a metric prefix that's written before the base unit. Okay? So what's the purpose of the metric prefix? Once again, it is to help communicate very, very large and very, very small numbers in such a way that you don't have a lot of errors. You minimize errors. So once again, metric prefixes is also for minimizing, if I can spell, errors. Okay? Scientists prefer metric prefixes. It's internationally recognized. So the metric prefixes are written with a base 10 in mind. So I'm going to go straight to it so we can see the chart that we have right here. So looking at these prefixes, these are not the most current prefixes. We have newer ones as computer storages are getting larger and machines are getting larger. We're able to see very, very small particles, and we're able to have a lot of storage. So we have newer, more recent metric prefix units that are larger than this, okay? So this table is divided into 2 parts. You have your large units and you have your small units. These prefixes here, tera, giga, mega, kilo, hecto, deca, these will accompany the more common base units we use. The common base unit we use here for weight or mass is gram. So you can have kilogram, megagram, decagram, hectogram, or meters, kilometers, megameter, very rarely ever used, liters, kiloliters, okay? Or for the same base units, these are the base units. For the same base units referred to here, you have the weight, you have the length, you have the volume. For these same base units for weight, length, and volume, you can use any of these prefixes, right? And I show it to you right here. For the weight, the length, and the volume, you can have decigram, centigram, milligram, any of these prefixes. So remember, with the prefix, you have the name of the prefix, or you have the symbol, or the actual value, okay? And these names or these symbol represent these numbers. So the most important thing, even though I have marked all over this, it's for you to recognize what the values of these prefixes are. And not only that, for you to be able to perform conversions. On the surface, this looks straightforward, right? But the goal here is not to go through King Philip. So we had to learn this mnemonic in middle school. King Philip drank cold milk and then something happened. I forget the rest of it. I think I should Google it at some point. But it was something about King Philip and he was drinking something and then something happened. I forget what happened. Okay? We're not trying to use that method where you're jumping from here to here to here to here. We're not using that method because we want to be able to do a lot more harder math. Okay? For that reason, when you have a problem, like I've written right here, let me erase this. When you're given a problem, the goal is for you to understand what the letter represents. So in our problem here, this very simple problem, you are being asked to go from 1 hectometer to a meter. In our problem here, you want to check and see how many metric prefixes do you have in this problem. I look over here and I only recognize this as my metric prefix. So what's the value of H? I look over here. Oops, wrong thing. Wrong. This. H stands for 100. So I say right here, I have one metric prefix is H, right? So from here, I'm actually going to write my own conversions. Sometimes they give you conversions, sometimes they don't. So I'm showing you how to use this table right here to get your own conversions. I write 1 hectometer, okay? This is a prefix that we're trying to define, is equal to, in the place of the 1 hecto, I actually write the value of what this is, okay? And I'm actually going to write it as a scientific notation. So I'm going to write it in this form. This is equal to 1 times 10 power. The H is actually 10 power 2 meters. So in the place of the 1H, I wrote this number here. Because the H stands for times 10 power 2. And remember, they asked you to remember these numbers as being 1 times the unit anyways. So we see it as 1 is this 1 over here. H stands for that. And I just rewrote the same number. And now I have my conversion factor. Okay? So once again, I am just writing an equality to define what H is. This is my equality. I got this from the table. Now that I have my equality, I can use my equality to perform my conversion. So I write 1 hm. I have my conversion right here. I write 1 hm on the bottom, 1 times 10 power 2 m on the top. Remember, put this in parentheses. This and this cancels out. My answer is going to be an m. Okay? So real quick, I write right here, 1 times, open parentheses, 1 exponent, 2 to the right, close parentheses, equal, oh, the same number, 100 meters. Okay, based on this question I made up. So this is what you do when you have one metric prefix. Okay, so I'm going to say here, I have one metric prefix. And the metric prefix was only in my given, right? So what do I do if I have two metric prefixes, like this scenario right here? So I created a complex metric prefix. Well, sorry, a complex scenario. which I created, and I'm going to get us out of that. So in this problem here, as is indicated, let me erase just that. I notice two metric prefixes, okay? Because I have a base number, and my base unit is G, my metric prefix is K and DA. My base number is G, as in grams. So before I do any kind of conversion, I have to write equalities that define what DA is and what K is. So the easiest thing to do is say 1 DAG, and then figure out what that is, and then 1 KG, figure out what that is. Okay, we're trying to get equalities that define or identify the metric prefix DA and the metric prefix K. So I have to go back to my table and figure out what does DA stand for. Go back here, DA. DA is 10 power 1, okay? And then K is 10 power 3, as in 1,000. Okay, I can do this. DA is going to be 1 times 10 power 1, right? And I write the G here. Don't forget to write the G. That completes your equality. And over here, I have 1 times 10 power 3. I'm writing in scientific notation. It makes it a lot easier. And I have this here, G. So I now have my two notations that define the metric prefix. All I have to do is set up my conversion and convert. Okay, so I have my given number. Ignore these in the bottom here. I have my given number, 0.17 DAG. I have to pick my next conversion. My conversion that works is the one that has DAG in it, DAG. Okay, so I'm going to use this one here next. 1 DAG, and this goes with that because they're a combo. 1 times 10 power 1 G. Okay, this is scientific notation. Next conversion, I get to use this one here. So DAG cancels out with DAG, DAG and DAG is gone. And then since I have my next dominant unit is grams, I get to use that next. So I put the 1 times 10 power 3 on the bottom, grams right here, and 1 kilogram right here. Okay, so over here, let's see. Oh yeah, grams and grams cancel out. So when I work this out, guess what my answer works out to? I get my answer in kilograms. And hopefully this wasn't that overwhelming. In the past, people would get stuck right here. How do I go from that to that? I can't use my little, skip thing, I'm trying to use my hands to show. It's hard to describe what we used to do in middle school, but we used to do it and it worked. Okay? So, okay, you see this answer, pretend this never happened. We're going to work this out from scratch for ourselves with this new font right here. Okay? So you're going to take 0.17 times, let's see, 1 times 10 power 1, and then divided by, I'm ignoring the ones, 1 times 10 power 3. I want to write it as is because I want to have zero error. So on my calculator, 0.17 times, open parentheses, 1 exponent, 1 to the right, close parentheses, divide by, open parentheses, 1 exponent, 3 to the right, close parentheses, equal. After all that, I get 0.0017. Okay? So this is what I get for my math. I mean, of course, they have all of this stuff here showing you how they did. And when I say they, I mean me. This is me in the past. But anyway, I did that, and this is what I get, 0.0017 kids. The method is key, right? Remember, this chart here is very useful. Not to say that charts in other classes are not, but in chemistry, pictures teach you a lot, and they usually have a lot of information that are very helpful. So remember to be able to create equalities for yourself out of these metric prefixes based on the number of prefixes given to you in a problem. Now, let me see. I like being a little random, so let me see. Mass, weight. Let's finally go to that one set of questions that I have been wanting to use this whole time, okay? I've been waiting for us to do this conversion right here. Look at that. Look at all of these. I'm a little excited, okay, because I've been waiting for this time. Okay, so now I have this here, right? I'm trying to see how I can convert this. Can I copy this? Can I cut this? Maybe I can. Okay, so we won't do all the conversions, but let me see if I can. Actually, let me see. The downfall of these headphones, I'm hearing all my emails really loud and clear. Okay, let me see if I can actually just cut this whole thing. Oh, not gonna work. Okay, I'll do it step by step. Let me just take these right here, and we will put this on the other page because I want us to be able to see the conversions, right? I'm gonna cut this here. Why is it not allowing me to take it over? Okay, now it's okay. Hold on a second. Let me see. But it's not working. Anyway, let me write it down real quick, and then we'll go ahead and copy over. I'm gonna have us do the first one since we've done something with DAG. We're gonna go ahead and do this one here, and then we'll do. I want us to do this one here. Okay. So in this part here, I'm actually gonna just write it right here. We're given 5.6 times 10 power negative 7, right? Hectometer, 2 meters. Since we have just HM, 2 meters, what I'm going to do is I'm going to actually have you guys work this out and then tell me what the answer is. And then we'll go from there. Because I normally do it myself and you guys watch, but let me have you guys participate. Can you guys go ahead and I'll give you guys a minute to work it out. So please write this down. And I'll go to the other page so you can see what the H value is. We have to figure out what H is. And then if someone can walk me through what to do, that will be perfect. Okay? So we have 5.6 times 10 power negative 7 HM 2M. What do I do? I'm going to go back to this other page here where we have our PowerPoint. So we can see what the value of H is. We're right here. Yes. Okay, I guess what I can do here to make it easier. I can add a page. So we're not going back and forth. Okay, so the value is 5.6 times 10 power negative 7 HM 2M. So what do I do? You can text it in, you can say it, just somebody give me directions.
Okay. Well, personally, what I would do first is that I tried to I mean, to simplify it for me, I changed the 5.6 times 10 to the negative 7. I decided to like put it in its base form, you know.
Okay.
So let's do. Well, I'm going to. Sorry if you hear the
Okay.
rain.
Okay.
If
Oh, it's raining over there?
oh yeah, it's raining pretty bad. So
Okay, so you're gonna convert it to the base form. Okay.
that's
But then how
hectometers.
do you get from hectometer to meters?
Well, because so we're gonna. Okay, so let's use that conversion uh factoring you were mentioning.
Uh-huh.
Okay, so 0.000056 hectometers and 100 meters equals 1 hectometer. And of course, you put
Okay.
1 hectometer diagonal
So,
on the point
so say
zero
one
zero
one
zero.
hectometer equal 100 meters.
Yeah.
Okay. So you
Oh,
got that
sorry.
from here.
I did the fraction. I did the 100 meters over 1 hectometer.
Oh, okay. I see what you're saying. 100. So you already have them in this form. 100 meters over 1 hectometer, like that.
Yeah, and diagonal from the hectometer,
Okay.
top
So then
left would be
5.6 times 10 power negative
yeah,
7 hectometer, and I'm assuming you're saying this, right? 100 meters and then 1 hectometer. Okay. Then what do I do here? I'm
okay.
pretending I'm stuck. I'm not really stuck. Well, I don't know. Let's say I'm really stuck. Then what do I do?
In that case, so I still have it. I still have the 5.6 as hold on,
The standard form, the decimal
yeah,
form.
yeah,
Okay.
yeah.
So then the
So
HM and the HM cancel out, right?
yeah,
Okay. And then your answer is going to be some number in meters, right? Let me move this out of the way. But yeah,
yeah.
your answer will be some number in meters. But what is this some number?
So that would be okay. So if it's in meters, it's point. It's there's four. So point 0.000056.
Wait, how many
But
zeros?
then you can convert that.
One,
Yeah,
two,
four.
three,
Yeah, four
four.
zeros. So then once you return it back, 1, 2, 3, 4. Okay, that would equal 5.6 meters times 10 to the negative 5.
Right. Very good. Yeah. Hey, if you have a longer method where you're more comfortable, go ahead and use that. Okay. If you have a longer method, but you're more comfortable with that, that works too. So mathematically, I'm going to show this to you. 5.6, another way, this is an or. 5.6 times 10 power 7, or negative 7. If you use a scientific form, scientific nature of this, and then you multiply this by, let's say, 1 times 10 power 2 over 1 hectometer, that works too, right? You write it as 5.6 times 10 power negative 7, and then the 1 does nothing. You're bringing in a times 10 power 2. Mathematically, these two add up. Let me see, this is M. I forgot a unit right here. Bad teacher. That's me. I try to discipline myself so I can use units. Okay. Negative 7 plus 2 gives you 5.6 times 10 power negative 5 meters. Okay. So there is that too, and that works.
Oh, okay. That's a lot easier.
Hey, I'm trying to show y'all different ways to solve this. Pick a way that works for you, that gives you the right answer, and stick with that. Okay? Okay, let's do the next one. So this is my list of questions I'm so excited about. I don't even know why I'm excited, but I am. Here's my next one here. Because I want to make sure, once again, y'all's homework does get interesting sometimes. That's the term I'll use. 9.6 times 10 power 6 dg 2 kg. Okay, so this is what we're working on. Once again, back here, because I want to see the conversion, right? The conversion page. So I'm going to add the page right under there because I need to see it right here. Okay, right here. Where was I? So we're working on 9.6 times 10 power 6. We're going from dg to kg. What do we do this time? Let me erase all these marks I have here. What do we do? I need your help. How do I solve this? Anybody? Mm-hmm.
Um, I,
You may as well.
okie doke. So, okay, let's see what we can do first. So, okay. I remember the way you did it earlier. Trying to make sure. Okay, so I might do it my way again real quick before, because that's the way I know how to do it right now.
The
So,
one with the decimal?
no,
Let's
may,
see. When you're
or
changing
you can
the
re-show how you did it.
scientific notation to what is it called? Standard numbers. So wait, y'all want me to do it again? Well, this is not a good relationship.
Hold on. Okay, Dessa. Okay, so Dessa. Okay. So that's
Yeah, this one right here.
okay.
This one right here. That's this, yeah. So all you're doing is trying to get an equality from
First.
this. So you just say, you always write 1. Keep it simple. So 1 dg equal what grams? So what does a 1d stand for?
1 decigram is equal to 0.1.
Okay, you can use this form or you can use either form anyway. Since he's telling me what to do, I write 0.1. Okay, that works. Either number, the left one or the right one. See, if I do it my way. If you guys do it, then you're bringing in your way, and maybe that may be helpful to somebody else. You know, that's why I really
Okay.
encourage y'all to help me. Okay, the other conversion, since we have 2 prefixes, right? 1 kg equal what? What does
100.
K stand for?
Oh,
K.
100.
You mean this number,
Oh,
100?
1,000. Oh, yeah. Sorry. Wow. Oops. Wow. Brain fart there. Okay.
That's okay. That's okay. You were rushing to the answer, so right.
Yeah.
Okay, we got that. So we got those 2. Once you got those 2, the rest of it is simple, right? So now you just write your number, 9.6 times 10 power 6 dg, and then you have your conversion right here. Let's see. Oops. Since we have a dg right here, the next conversion you pick must be dg. So it's going to be 1 dg, 0.1 grams, right? Because these go together as a combo. And then DG and DG cancel out. Now you have to pick something that has grams in it. So we have 1,000 grams, 1 kilogram. And so gram, and let's see, we get our answer in kilograms, right? Versus guessing. Like before, that one method where you skip from one number to another and you kind of count, I wasn't ever sure whether my answer was right. With this one here, I feel pretty confident. Well, as long as I input it correctly in my calculator, I feel pretty confident after that. Times 0.1. So I have open parentheses 9.6. Then I have my exponent button 6 times 0.1 divided by 1,000. Let's see what we get. It says I have 960 over here. Okay, 960 kilogram. Yeah. Okay, before I go back to that page and work a couple more, I want to do the one that I copied from earlier. Remember the one that I kind of copied over? This is when you're starting off with, instead of having a simple number, you're having a fractional number. Say 32.7 kilometers per liter. And they want you to convert from miles to centimeter cube. Like I said, the beginning was a warm up. Now this is chemistry. Okay. The way you work this out, we recognize we have a complex measurement, right? The top part, which I'm going to highlight, kilometers, miles. These are both length. Bottom part, liters, centimeter cube. These are both volume. For that reason, we will go to our length part and get a length conversion that relates the yellow parts together, okay? So I'm going to go to length. This is why I had this stuff over here, okay? Length right here. Do I have a kilometer and mile equality? Kilometer, meters, no. Kilometer, no. Oh, there it is. It's reverse of what I want, but as long as they're related, this works. So I'm going to pick this out. Oops, wrong writing too. 1 mile equal 1.609 kilometers. Okay, I got that down. And then I need one with a volume. So I'm done with this part. I need a volume conversion. I need something that has liters and centimeter cubed. Okay, 1 meter equal 1,000 liters, no. 1 decimeter cubed equal 1,000. Oh, but this second half is what I need. Or down here, 1 liter equal 1,000 centimeter cubed. This is what I need right here. 1 liter equal 1,000 centimeter cubed. It takes a while to get the hang of it, but once you get the hang of it, it's so easy to come here and pick the right conversion factor, right? Okay, now I got the 2 conversion factors I need. I'm back to my screen. What do I do now? Well, convert. 32.7 kilometers is the top part. I'm going to write this out as a fraction. My bottom part will be liter, but I don't want the liter to be lonely, so I put the number 1 here. It doesn't change the top value. Now we have 32.7 kilometers over 1 liter. Okay? So what conversion do you want to start with? Length, volume? Let me try to mix it up, okay? Because I do this a lot. I'll start with the volume. If I'm starting with the volume, I'm starting with the bottom part. So the unit I pick has to have liters in it because I'm starting with the bottom part. That's my goal, right? So that means I have to use this conversion factor next. How will I use it? The units have to match diagonally across. So I'll put 1 liter up here, 1,000 centimeter cubed on the bottom. Why? The rule is the units have to match diagonally across. Okay, check. Plus, I'm kind of half done anyways because I got centimeter cube in the bottom, so I'm doing good. Okay, now I have to get rid of kilometers to bring in miles. So I'm done with this. I can now use the first the first conversion factor. I'm going to use this one here. I'll put 1.609 kilometers on the bottom because these have to match diagonally across, right? And then 1 mile goes on top. Plus, my final answer right here says mile has to be on top, centimeter cube has to be on the bottom. That's what I got right here. Mile on top, centimeter cube on the bottom. This and this cancel out. Ta-da! Okay? The rest of it is just math. So my answer will be some number, mile on top, centimeter cubed on the bottom. Now the math part, 32.7 times 1, it's implied, divided by 1,000, divided by 1.609. Okay, let's see what we get. 32.7 times, oh, there's nothing here, so times 1, divided by 1,000, divided by 1.609. What do I get? 0.0203. Oh, we haven't done significant figures yet, so I'm going to put it right here. 0.0203. Okay? That's the answer I get. Any questions about that? Like I mentioned earlier, the conversions, which is what we go over this chapter a lot, it takes some, it's really not that difficult, but you want to practice it to get the hang of getting different units. So I do have some more here, which we went over earlier. Let me see. I will do one more from here, and then the rest we'll do next time. Let me see. I don't want to do the pint. Y'all can work on that if you want. Oh, I actually want to do this one here. Sure. Let's do this conversion. So this is going to be 6.5 meters squared to centimeters squared. Okay. I had a student ask me once, why can't we just do that method where we do this? And I said, because how do you solve a problem like this one here? Okay. So let me see. I was somewhere in here. Does it really matter at this point? Not really. I'm just transferring the question over. Oh, it does matter because I want you guys to see the metric prefix. Okay, I forgot what I was trying to do here. Let me add the page right under here because I'm trying to show you guys the metric prefix. So here, we're going from 6.5 meters squared to centimeters squared. Okay. So if you look at meters by itself, meters is a length, right? So what they have us doing here is we're going from a length squared to a length squared. A length squared is essentially area, right? So from an area to an area. Now, had they said length cubed to length cubed, then we would know we're going from a volume, because volume is essentially length cubed, to a volume. But they said squared. So this is what we're dealing with. So what I'm going to do is not guess. I'll go over here and see. Do I have a category for area? No, I have length. I have mass. I have volumes. In volumes, all the length measurements are cube. This is cube, cube, cube. This is not what I'm looking for. Cube, cube. Once again, cube, cube, cube. Yeah, this is not it. So what do I do? Essentially what's shown here. Get the length conversion and then just square it. Okay, that's what they're saying here. So it's not that simple. What I need to do is, since I have a metric prefix here, I need to write an equality for metric prefix. I'm going to write it on the bottom. 1 centimeter is equal to some number meter. The centi stands for, so back here, 1 centimeter, centi stands for 0.01 or times 10, 1 times 10 power negative 2. So to make this simple, I'm going to use this number here, 0.01. Okay? So 1 centimeter is going to be 0.01 meter. You're free to use either the number on the left, this one here, the number on the right, they're the same number. Okay? So I got this equality from the table. Now I have to get length squared. So I got my equality first. Now I'm going to square, I'll say square both sides. Square both sides. Number and unit. So what I mean by that is square both sides. The number should be squared and the unit should be squared for both sides. So what I mean by that is 1 squared, centimeters squared. Don't square equal. Equal 0.01 square this, and then meters squared. We're squaring the number and the unit to generate. This is like a DIY conversion factor. There wasn't one available, so you made your own. Okay? By yourself. You square everything but the equal sign. Okay, what is 1 squared? 1 centimeter squared remains a centimeter squared. Equal is equal. Square this number here, 0.01. Well, you got to square it in your calculator. 0.01 square that is equal to 0.0001 meters squared. So it's very important that you get the right metric prefix from up here, right? I checked and I found out the centi was 0.01 of whatever it's put in front of. So yeah, square that. So I took the conversion I had from the table, this one here, and I made my own. This one. So now that I have the one I made, I can solve it. 6.5 meters squared. I can use the DIY conversion I just made. Oh, the meter part has to be on the bottom, so 0.0001 meters squared. And this part goes on top, 1 centimeter squared. And yep, this works out, and then you work it out. That's why this method is taught at this level, because they want you to be able to solve a lot of problems. Okay, so the mass is 6.5 times 1, if you want to include 1, divided by 0.0001. And your answer will be some number centimeters squared, right? So let me work this out. 6.5 times 1 divided by 0.0001. Okay, so I get 65,000 centimeters squared. Ta-da! This is the answer. Yep. Any questions about this? Yeah, I started slow, I started easy, and then we got right to it. So recognize that they can ask you to square units. That is viable. They can ask you to do that. It is possible. I don't remember your homework questions, but I have seen some in the past where they squared stuff. So if they ask you to square units and you recognize the units, just make sure if you have the equality, you're squaring both sides. Okay? Any questions about this? Let me see what else is in the chapter before I get lost in that worksheet, because there's a lot. I know we covered a lot. We didn't do that part, but we covered a lot. Oh, this is just telling you, let me see, because my goal is usually to kind of get close to half. Oh, this is just telling you here the unit. So this is somewhat, I shouldn't say it's not important, but this is more FYI information saying that when you're in the lab, you usually have to measure the mass. The mass and the weight are technically the same thing. The mass is the measure of the quantity of matter, while the weight has to do with the gravitational pull of the earth on the person, right? But in chemistry, when we use the term mass interchangeably with weight, in physics, these are not equal. In chemistry, it's okay to consider the mass and the weight as the same thing. Okay? What do we use to measure the weight in the lab? Well, you have different instrumentation, and I showed you here. The one on the right is more precise and very expensive. If you look over here and you look here, look at the number of decimal places. One, two, three, four. 4 decimal places. You pay a lot of money for each decimal place that you're paying for right here. Each one of these costs you extra money. Okay, so we do have a scale like this on our campus, but we use the scale for the organic lab where we're synthesizing, we're making compounds, and so we need to be able to measure every amount. Do you see the shield over here? Because the scale is very sensitive, how do I know it's very sensitive? It measures to 4 decimal places. If the wind is blowing, the wind, or if somebody's breathing very hard, you can lose some sample, and so the shield here shields the sample from air currents, including your breathing. People get nervous, like, oh my goodness, they breathe hard, and then the sample falls off. Okay, so this barrier here is to shield your sample from air currents that can change the mass. So if you have one of these open, you will see this number here changing all the time. It's very sensitive. Pharmaceutical companies, where they make drugs, they use this kind of scale. In the lab, we have this scale here. We also have this one for organic. We have this scale here for general chemistry, and then that scale. This scale B, is basic electronic. It does measure the value to 2 decimal places, so it has some level of accuracy or precision without being super expensive. So we're talking about maybe 250 gram. Not sorry, 250 as in cost. Sorry, the cost of this is about $250. And then right here, this is about maybe 2,000. Okay.
Oh.
And then this, right, you're paying for the precision, for the decimal places. This one here, I would say maybe $50. This is old school, $50. Not that expensive, okay? It's less precise. You more likely will have a lot of errors with this because it depends on the user and the skill that you have using this. But yeah, this tends to be more precise. So they use this in the DEA, in pharmaceutical companies and stuff, okay? When you're measuring the mass, it's measured in kilograms or grams. In the lab, it's usually measured in grams, and then we convert this to kilograms, the base unit. And of course, when it comes to length, sorry, we may measure it in centimeters or meters, and we convert to centimeters or millimeters, and then we convert this to meter whenever necessary. So I won't go over any, well, let me see. Yeah, I guess I'll go to this point right here, to this slide right here, and then I'll stop, because at some point I want us to read measurements from equipment, and I'll have that available in our next class on Thursday. So right here, just real quick, we're told that the SI unit for the volume is cubic meters, so just be aware of that. And they show you here how they get the cubic meters. So just be aware, it tells you right here, the cubic meters, 1 meter cube, essentially related to different conversion factors right here. And you can see that, where's my conversion factor list? Right, you have 1 meter cubed equal 1,000 liters. So we have a conversion factor here comparing meter cubed to other measurements. You have liters compared to centimeter cubed. So once again, just be aware, most of the time in the lab when we're measuring volumes, we measure it in milliliters. The milliliter, 1 milliliter, equal to centimeter cubed. So just be aware of that. It's a conversion factor, yeah, right here. 1 milliliter equal to centimeter cubed. So in the lab, we tend to measure volumes in milliliters, and then as needed, we convert it to centimeter cubed. 1 milliliter equal 1 centimeter cubed. So just be aware of that. The basic units in which the volumes of liquids and gases are communicated is usually either liters or milliliters. And if necessary, they can be converted to centimeters cubed. Okay? Over here, all they're doing with this picture is defining the equality between the inch and the centimeter. And the idea is, if you look at this inch, the inch goes all the way here. I did this injustice. So the inch goes, oops, all the way here. Okay. So if you look at the inch from here to here, this is 1 inch. But if you look at the centimeter side, the 1 inch is equivalent to 2.54 centimeters. And this is how they get the equality, right? The same object is measured twice or measured using different measurements. So 1 inch from this picture is defined as 2.54 centimeters. Okay? So we'll look at the rest of this chapter once again on Thursday. Does anybody have any questions? If you don't have questions, oh, sorry, yeah?
I think we're good.
Oh, you're good? Okay.
Yeah.
If you don't have any questions, I'm pretty much done for today. I mean, I did bring in a lot of questions and stuff like that, but the goal is the PowerPoint doesn't have a lot of questions, so I have to bring in some extra questions, but we'll go over the rest of this chapter on Thursday. And I'm writing a note for myself so I don't forget to get pictures of graduated cylinders, so that we can make sure we're comfortable reading the estimated value. Okay? Yeah. So this is all I have for today. I'll see you guys on Thursday, right? It's Thursday?
Yeah.
Okay. Okay, that's it.
Well, appreciate
Thank
your
you.
time.
Okay, you're welcome.
Yeah.
Remember where
Thursday.
I had
Oh.
okay, see, it says it. Remember where I had this posted, right? I found it right here.
Isn't it underneath like the assignments tab on that like yeah.
Yeah, it's right here too. Just in case, feel free to download it. It is a very helpful resource. Okay?
Okay, cool.
Okay.
Yeah. Oh, okay. Awesome.